Section 1.7, Inverse Functions. Before we start discussing inverse functions, let's recall the following term that we learned in college algebra. A function is said to be one-to-one if each output value of a function corresponds to exactly one input value of that function. Another way to phrase this, for each y value of an ordered pair on the graph of the function, there's exactly one x value that will yield that y value. One of the ways we learned how to test to see if a function was one-to-one is using something called the horizontal line test. So to determine if a graph is one-to-one, we can use the horizontal line test, which tells us a graph of a function is one-to-one if and only if every horizontal line intersects the graph and at most one point. If we take the two graphs here in the figure to the rightmost graph fails the horizontal line test because we can see that this one horizontal line passes our graph at 2 points. So there is one output value of our function that is produced by two different input values. If we look at the graph here on the left, this will pass the horizontal line test, since no matter where we draw our horizontal line, it's going to intersect our graph at exactly 1 point. So each y value corresponds to exactly one x value. Now that we've gone over briefly what a one-to-one function is, now we can define an inverse function. For any one-to-one function, which we're going to call f of x equals y, a function f to the negative 1 of x, which we're going to read as f inverse, is an inverse function of f if f inverse of y equals x. One way we think of inverse functions is that we're switching input and output. If I'm trying to evaluate f inverse of something, I'm trying to figure out what x value I would plug into the original function that will produce that value I'm inputting into the inverse function. This only works for one-to-one functions, because if a function is not one-to-one, that means there is some sort of y that is produced by multiple x's. So in that case, if I were to evaluate f inverse of that particular y, I would have two different x values, meaning that f inverse wouldn't be a function. So keep in mind, functions only have inverses if the function is one-to-one. One big thing to pay attention to with the notation is do not confuse the f inverse of x with exponent notation. It does look like an exponent, but f inverse of x is not the same as 1 over f of x. So be very careful reading inverse function notation. If we know that f and f inverse are inverses of each other, then the following two properties are going to hold. First, f of f inverse of x will equal x for all x in the domain of f inverse, and f inverse of f of x will equal x for all x in the domain of f. We're going to talk a little bit more about what this means or how to interpret this once when we start seeing a few more examples of how to test to see if functions are inverses. Now we'll explore our definitions with the following example. In this example, we're going to use the table to the right to answer the following questions. The first question, is f of x one-to-one? In order for a function to be one-to-one, that means each output variable corresponds to exactly one input variable. If we take a look, 4 only corresponds to -2, 5 only corresponds to -1, 10 only corresponds to 0, 7 only corresponds to 1, -9 only corresponds to 2, 3 corresponds only to 3, -22 only corresponds to 4. We can see from the table that each value of our function is produced by exactly one input value, so our function f of x is one-to-one. Next, we're going to evaluate f of -1. Using our table, we can see that when x equals -1, our function is positive 5. So f of -1 equals 5. This fact will also help us answer the next two bullet points. The next bullet point states if f of x equals 5, then x equals blank. From our work in the previous part, we know that f of -1 equals 5, so when x equals -1, f of x will equal 5. The thing we have to be careful of, will there be another x that will satisfy the equation f of x equals 5? And the answer is no. Because we already know that our function f of x is one-to-one, then there is no other x value that's going to cause f of x to equal 5. Next, we're going to evaluate f inverse of 5. When we evaluate f inverse of 5, this is equivalent to asking if f of x equals 5, then x equals blank. Well, we've already answered this already. X would have to equal -1, which means f inverse of 5 equals -1. So that illustrates the mindset that we need when we're evaluating inverse functions. When we're trying to evaluate f inverse of a number, let's say a, this is equivalent to saying f of what equals a. If we look at the next bullet point, we're trying to evaluate f inverse of 4, which means we're trying to figure out f of what value would equal 4. If we go to our table, we can see that f of x equals 4 when x equals -2. So f inverse of 4 is equal to -2. Now we're going to determine if the following functions are inverses. The way we're going to tell if two functions are inverses is by seeing if they satisfy the property of inverse functions that we outlined back when we were defining inverse functions. That is, when we perform the function composition, f composite g and g composite f, both will give us x. One thing to keep in mind, we do have to check both compositions in order to show the two functions are inverses. So first we'll do f of g of x. G of x is x plus 2 over 3, which means everywhere I see x in my function f of x, I'm going to replace it with x plus 2 over 3. Now we can see some cancellation occur. The 3's will cancel first, then the 2's will cancel, leaving us with x. So f composite g does give us x, but that's not enough yet to conclude that they are inverse functions. Next, we'll do g composite f. F of x is the 3x minus 2, so everywhere in g, we're going to replace x with 3x minus 2. Now we'll proceed to simplify. Since there's nothing to distribute in the parentheses in the 3x minus 2, we can drop the parentheses. We see the 2's cancel, leaving us with 3x over 3. Then the 3's cancel, leaving us with x. So g of f of x will also equal x. One thing to keep in mind when you're testing to see if two functions are inverses is both compositions have to equal x. If one composition is not x, then the two functions are not inverses. Also, this example highlights the relationships between functions and their inverses. With f and g being functions, notice how when they simplified, a lot of things canceled out. We can think of inverse functions as functions that undo each other. That is, function f will change x into something, f inverse will change that something back to x. Next, we're going to test to see if f of x equals the cube root of x minus 4 and g of x equals x cubed plus 4 are inverses. Once again, we'll do the function composition. First, we'll do f of g of x. G of x is the x cubed plus 4. So everywhere in f, we're going to replace x with x cubed plus 4. And we have the cube root of x cubed plus 4 minus 4. Just like before, I did put parentheses around the x cubed plus 4, but they are not needed. So we'll go ahead and drop them. Now we can see the 4's cancel, and we need to take the cube root of x cubed. Now, because any real number has precisely one cube root, then the cube root and the cube are going to cancel, and we're left with x. Now we'll do the reverse and find the composition of g and f. So we're trying to find g of the cube root of x minus 4, which means everywhere in g that I see x, I'm going to replace it with the cube root of x minus 4. By definition, when we cube a cube root, the cube and the cube root effectively cancel, and we have x minus 4 plus 4. The 4's cancel, and we get x. So we see both compositions yield x, so these two functions are inverse functions. Next, we're going to test to see if f of x equals x minus 5 squared and g of x equals the square root of x plus 5 are inverse functions. First, we'll find f composed with g of x, which is f of the square root of x plus 5, which is the square root of x plus 5 minus 5. Nothing to distribute, so we can drop the parentheses. 5's cancel, which leaves us with the square root of x squared. And by definition, the square root of x squared would just be x. So far it's looking pretty good that these two functions might be inverses. But let's check the other way around. Now we'll find g composed with f of x, which is g of x minus 5 squared. Now, this is where we have to be very careful. It is very tempting to want to say the square and the square root cancel. However, this isn't completely correct. The square and the square root don't actually cancel when the square root is outside and the square is inside. If we were to take a look at an example, if I take the square root of 2 squared and follow the order of operations, that would equal the square root of 4, which equals 2. So it seems like, okay, the square and the square root cancel, at least when I plug in 2. However, if I perform the square root of negative 2 squared and still follow order of operations, this would equal the square root of 4, which equals positive 2. In general, the square root of x squared is not actually x. The only time it's going to be x is when x is either 0 or positive. If x is negative, the square root of x squared is actually going to be the opposite of x, which we denote as negative x. And if you recall from college algebra, the function that is defined to be x when x is greater than or equal to 0 or negative x when x is less than 0 is the absolute value function. So the square root of x squared is actually the absolute value of x, not actually x. So turning our attention back to g composite f, the square root of x minus 5 squared is actually the absolute value of x minus 5. And unfortunately, there's no way I can simplify this any farther. And that's because I don't know the sign of x minus 5. X minus 5 could be positive, in which case, sure, I can drop the absolute values. Or x minus 5 could be negative, which means the absolute value of x minus 5 would be its opposite and wouldn't simplify to x. From our work, we know f composite g of x is x, but g composite f of x fails to equal x. So these two functions are not inverses. It also makes sense that these two functions would not be inverses. If we think about the graph of x minus 5 squared, we know that would make a parabola which is not 1 to 1. So of course, f shouldn't have an inverse. Now, under certain conditions, such as restricting the domain of f of x, we can make these two functions inverses. We will discuss that a little bit more later, how we can restrict the domain of quadratic functions so that way they are invertible. Next, we're going to discuss how to obtain the graph of an inverse function. If f is 1 to 1 and the point AB is a point on the graph of y equals f of x, then the point BA is a point on the graph of y equals f inverse of x. The reason why this is true is in order for the point AB to be on the graph of f of x, that means f of A would have to equal B. Since f is 1 to 1, we know that f would have an inverse, and by definition, f inverse of B would have to be equal to A. So the point BA would have to be on the graph of f inverse of x. This relationship between the points of f and f inverse causes the graph of y equals f inverse of x to be the image of the graph of y equals f of x to be reflected over the line y equals x. Using this information, we're going to take the graph of f of x below and graph its inverse. Our function will have an inverse because no matter where I draw a horizontal line, we see that the horizontal line will only intersect one point. So our function is 1 to 1. To graph the inverse, we'll start by identifying key points on our graph of f of x and then interchanging the x and y coordinates. Our first point here at the bottom left is the point -6, -2. When we switch the x and y components, we obtain the point -2, -6. If we take the point 0, 0, which is a point on our original graph f of x, if we switch the x and y components, since the x and y components are the same, 0, 0 is going to stay in place. Taking a look at the topmost point, that is the point 8, 9. When we switch its x and y components, we obtain the point 9, 8. As for the graph of our inverse, we know that the graph of our inverse is the image of our graph of f of x reflected over the line y equals x. In green, I've drawn the line y equals x. Now we're going to connect our blue dots together, so that way our blue graph of f inverse, is the mirror image of f of x. Since the point -6, -2, and 0, 0 were connected with a straight line, I'm going to connect the -2, -6, and the 0, 0 with a straight line. Notice how the 0, 0 and 8, 9 are connected with an arc that is bending away from our line y equals x. Then I'm going to connect the corresponding points 0, 0 and 9, 8, also with an arc that looks like it's bending away from the line y equals x. So in blue, there's my graph of y equals f inverse of x. Next, we're going to discuss how to find the inverse function of a function defined by a table. On the left, we have a table that defines f of x. We can see that f of x is 1 to 1. Each function value corresponds to exactly one x value. Our goal is to figure out the table for our inverse function, f inverse of x. We're going to use the same idea to fill out this table that we used to create our graph in the last example. That is, if f of a equals b, then f inverse of b equals a. Since we have the row -2, 4, meaning when x equals -2, f would equal 4, that tells us when x equals 4, f inverse equals -2. We're just switching our x and f of x values in order to obtain x and f inverse values. So the row -1, 5 on the table for f of x tells us we have the row 5, -1 for f inverse of x. And we'll keep doing this for each row in f of x. So we'll have 10, 0 for f inverse, 7, 1, -9, 2, 3, 3, and -22, 4. And there's our table for f inverse of x. Now we're going to find the inverse of a function when the function is defined with an equation. We're still going to use the same strategy we saw with graphs and tables, where x and y components switch. So to help us find the inverse, we're going to use a strategy that we're going to call the switch and solve strategy. The switch and solve strategy is a 4-step process. Step 1, we're going to replace the f of x with y, so that way we're no longer looking at the function notation. So f of x equals 3x minus 2 becomes y equals 3x minus 2. Now step 2 is the switch part of our strategy. We're going to switch x and y. So anywhere I see a y, I'm going to replace it with x. Anywhere I see an x, I'm going to replace it with y. And my equation becomes x equals 3y minus 2. Step 3 is the solve portion of our strategy. In step 3, we're going to solve for y, meaning we want y by itself. So first we'll add 2 to both sides, and then we'll divide both sides by 3. Step 4 is to write our resulting equation in function notation. Since our function was originally named f, what we just found was f inverse of x. So our inverse function of f is x plus 2 over 3. If you weren't confident in finding your inverse, you can check by composing f with f inverse and f inverse with f to make sure you get x for both compositions. It's very similar to what we did back in example 2. Next, we're going to find the inverse function, if it exists, of g of x, which equals 7e to the 5x. So our function g of x here is exponential. Finding our inverse is still going to be the exact same process we did in the last example. Step 1, in our switch and solve strategy, we'll replace our g of x with y. Even though my steps above use f of x and f as our function, they still apply to g or any name we choose for our function. Now we move to step 2, where we switch our x's and y's, and we have x equals 7e to the 5y. Now to solve for y, we'll start off by dividing both sides by 7, and we get x over 7 equals e to the 5y. Since our right-hand side is exponential, the way we get rid of the base e is we apply the natural log to both sides of the equation, and we get natural log of x over 7 equals 5y. If you recall from college algebra, the natural log of a number represents the power that we have to raise e to obtain that value. So e to what power gives us e to the 5y? That would be 5y. Now that we've gotten rid of e, we can finish solving by dividing both sides by 5. And we get y equals natural log of y over 7 all over 5. Step 4, we'll rewrite our equation with the function notation. Since our function was originally called g, we're going to call our new function g inverse. So g inverse of x equals the natural log of y over 7 all over 5. Now we're going to find the inverse of h of x, which equals the cube root of x minus 3 plus 2. Following our switch and solve strategy, replace our h of x with the letter y. Then the switch, we switch our x's and y's. Now we solve for y. Start off by subtracting 2, cube both sides to get rid of the cube root. And we're not going to worry about expanding our x minus 2 to the third. We'll leave it as x minus 2 cubed. And then to finish solving for y, we add 3 to both sides, and we get x minus 2 cubed plus 3 equals y. Then we replace the y with our function notation. Since our original function was h of x, then we found h inverse of x, and h inverse of x equals x minus 2 cubed plus 3. And next, we're going to find the inverse function, if it exists, of f of x equals x minus 2 squared plus 3. Still following the switch and solve strategy, replace the f of x with y. Now switch the x's and y's. Now we can solve for y. Start by subtracting 3. Now we need to take the square root of both sides. But we have to be very careful. Whenever we take the square root of both sides, we have to remember a plus or minus. Anytime we take an even root of both sides of an equation, it's important that you remember the plus or minus. What the plus or minus tells us is that y cannot be a function of x. This is because for any x in this equation that we have now, we're going to get 2 y's. So the plus or minus tells us there's no inverse function of capital F of x. We could tell sooner that f of x would not have an inverse in this problem. If we think about the graph of f of x, it would be a parabola. Parabolas are not 1 to 1. So it makes sense that there is no inverse. But if we're not thinking about the graph, we can tell that there won't be an inverse if we run into a situation where, as we solve, we need to use a plus or minus, which, if you recall from college algebra, was an indicator that an equation did not represent a function. Thanks to the relationship between functions and their inverses switching x and y components in their order pairs, we have the following relationship between the domain and ranges of a function and its inverse. The range of a function f of x is the domain of f inverse of x. On the other hand, the range of f inverse of x is the domain of f of x. So to summarize, the domain of one function is the range of the other and vice versa. If we take a look at f of x equals 2x minus 3 over x minus 3, if we were to find the domain of f of x, we know the one number we can't divide by is 0. So x minus 3 cannot be 0, which means in order for our function to be defined, x cannot be 3. So our domain of f of x is going to be negative infinity to 3, union 3 to infinity. And this is no different than what we've learned in college algebra. What's different, though, is how do we find the range of f? If we can find an inverse function of f of x, then our range of f would equal the domain of f inverse. So let's see if we can find an inverse function to f of x equals 2x minus 3 over x minus 3. We'll start using our switch and solve strategy. So we'll replace the f of x with y, then we'll switch x and y. In this equation, it's particularly challenging to solve for y because right now we have two y's. One of the y's is in the denominator. So to help us solve, we'll start off by multiplying both sides of our equation by y minus 3. On the left-hand side, we'll distribute x. On the right-hand side, the y minus 3's cancel. Now keep in mind, we are trying to solve for y. So I want to get all my y terms on one side of the equation, which we can do by subtracting 2y from both sides. And at the same time, I want to get all my non-y terms to the other side, which we can do by adding 3x to both sides. And again, keep in mind, we're trying to solve for y, which means I want just a single y to appear in my equation. If I look at my left-hand side, which is the only side that contains y, we can see both terms have y as a common factor. So I can factor out y. Then I can divide both sides by x minus 2 to isolate y. And we get y equals 3x minus 3 over x minus 2, which means f inverse of x equals 3x minus 3 over x minus 2. The reason why we found f inverse is so that way we can find its domain, because its domain will be the range of our original function f. Looking at our f inverse, we see that it has division. The one number we can't divide by is 0. So x minus 2 cannot be 0, which means x cannot be 2. So our domain of f inverse of x will be negative infinity to 2 and union 2 to infinity. And since that's the domain of f inverse, that will also be the range of f. Now, we've seen quite a few examples with quadratic functions not being one-to-one and not having an inverse. In this example, we're going to look at how we can truncate the domain of functions in order to make them one-to-one. And we're going to start specifically with quadratic functions. If the vertex of a quadratic function f of x is the point hk, then f of x is going to be one-to-one on either of the following two domains. Either the interval h to negative infinity, which would represent the right part of our parabola, or negative infinity to h, which represents the left part of our parabola. For functions in general, we would use key properties to help us determine where to truncate the domain, and we'll see more of that later when we discuss trigonometric functions later on in this course. But right now, we'll take a look at f of x, which equals x minus 2 squared plus 3. We know on its natural domain, without any restrictions to it, this function is not one-to-one. But we know its vertex is the point 2, 3. And if we were to roughly sketch the graph, it would be a parabola that looks kind of like that. Next, in the first part, we're going to find the domain for which f is a one-to-one function and is non-decreasing. Then we're going to find the inverse function on that domain. If we take a look at our rough sketch of our function, on the left of our vertex, our function is decreasing. Since we want it to be non-decreasing, that means we want the domain that will represent the right part of our parabola. So our domain of f will be the interval 2 to infinity, representing the vertex and the points to the right of the vertex. Now we're going to use the switch and solve strategy. So we're going to replace the f of x with y, and we're also going to keep track of our domain of f, but we're going to do that using the inequality notation. So the interval 2 to infinity, being our domain, is represented with the inequality x is greater than or equal to 2. Now when we do the switch part of our strategy, we are going to switch x and y in our equations like before, but we're also going to switch the x in our inequality, representing our domain, with y as well. So the x greater than or equal to 2, which was the domain of f, when we switch the x with y, becomes the range for f inverse. Now from here, solving for y, we would follow the same steps that we did in example 5, since we're working with the same equation. And using those same steps, we would get plus or minus the square root of x minus 3 equals y minus 2. Before we stopped because of the plus or minus, but we're going to finish solving and then figure out how to resolve the issue with the plus or minus. So we'll add 2 to both sides, and we have 2 plus or minus the square root of x minus 3 equals y. Now, looking at the fact that y is supposed to be greater than or equal to 2, that's going to help us determine whether we should use the plus or minus. Keep in mind, the square root of a number is always positive. So if I do 2 minus something positive, I'm going to get a value smaller than 2, which means the minus cannot be used. But if I do 2 plus something that's not negative, I'm going to get something that's 2 or larger. So the y greater than or equal to 2 tells me the correct sign I should use in the middle is plus. So my f inverse of x on this domain of f of x is 2 plus the square root of x minus 3. And since I've resolved the plus or minus using the y is greater than or equal to 2, I don't have to write the y is greater than or equal to 2 anymore. But here we found the function of f of x once when we've truncated our domain. In the next example, we're going to find the domain of f of x, where f of x is one-to-one and non-increasing. Then we're going to find our f inverse of x. Taking a look at our graph, the right-hand side is increasing. So this time, we want to use the domain that represents the left part of the graph. So our domain of f that we're going to use to represent the part of our graph that is 1 to 1 and not increasing will be the interval negative infinity to 2. Now we'll follow our switch and solve strategy just like what we did before. Place our f of x with y, but this time, because our domain is negative infinity to 2, our inequality representing our domain will be x is less than or equal to 2. Now we'll switch our x's and y's, not just for our equations, but also our inequalities. Then we can solve for y using the same steps we would use in example 5 and the same steps we used above. And we would get the 2 plus or minus the square root of x minus 3 equals y, but this time y is less than or equal to 2. So thinking about what sign I should keep, the plus or the minus, I would look at the fact that I want y to be less than 2. Again, the square root of x minus 3 is non-negative. If I take 2, add a non-negative number to it, I'm going to get something bigger than 2. But this time I want something smaller than 2. So I don't want the plus. But if I do 2 minus something that's non-negative, it is going to make it smaller than 2. So here I do want to keep the minus. So my f inverse of x this time is 2 minus the square root of x minus 3. So whenever we truncate the domain of functions that are not 1 to 1 in such a way that makes them 1 to 1, based off of how we truncate that domain, it will have an effect on what our inverse function is. You can see just by having two different domains, we wound up with two different inverse functions. So be very careful about the domain of non 1 to 1 functions.